Before we begin, a quick disclaimer. This project is funded by the European Union. You can read this here. Views and opinions expressed are, however, those of the authors only and do not necessarily reflect those of the European Union or CBE JU, that is the Circular Bio-Based Europe Joint Undertaking, which is the funder Horizon Europe and the CBE JU of this project, MoeBIOs, and of the 3 projects in this cluster. Neither the European Union nor the CBE JU can be held responsible for them. So here's today's structure. There's one moderator, that's me. There are 2 excellent speakers. We have Gemma Figuerola Miró, optician and optometrist at Leitat, and Carles Musoll, AI, computer vision and R&D engineer at PICVISA. If you please could mute yourselves when you enter the room, that would be great. There will be a presentation by both of them, which will be recorded. We are recording this right now. And finally, at the end, there will be a Q&A session, which will not be recorded. So we will stop the recording at the presentation. So you can listen back to the main talk later, but the Q&A will stay in this live space. And the presentation will be uploaded to our Zenodo community of MoeBIOs, and you will see the link soon in the chat. So this talk is the first in a series, as I said, running on bioplastics recycling from the 3 projects, and we aim to contribute to advancing the technologies and processes on the recycling of bioplastics and contributing to as well the whole bioplastics market. So these talks will run from September 2025 to March 2026, and today is our first one, as I presented already, near technologies and digital tools for collecting and sorting bioplastics, and we will remain on topic for our next one as well on the 7th of October, with a more emphasis on the AI, bioplastic sorting and digital tools empowered by AI, and we will continue on 4th of November, and we'll dive into design for recycling criteria for bioplastics packaging. Quite crucial at this moment in time, and there's more to come in the months ahead, so stay tuned and we will keep you updated. So today, finally, we are joined by 2 experts from the MoeBIOs project, Carles Musoll from PICVISA and Gemma Figuerola Miró from Leitat, and they will share insights into near-infrared sorting and digital tools that are advancing the collection and sorting of bioplastics. And with this, and some housekeeping rules, please, as I just mentioned, keep your microphone muted, keep your camera switched off, and remember that AI tools on private recordings are not welcome here. For questions, you can either raise your hand and write them in the chat, and we will address after the talk during the Q&A that it would not be recorded. And with this, I leave the floor to Gemma and Carles. Thank you very much for coming here today to present all about your expertise.
So first, thank you, Stella, for inviting me in this talk. So hello everyone, and thank you for being here today. I would like to talk about something that at first sounds very positive, bioplastics, but which actually could create some headaches in waste sorting and recycling. Gemma, can you give me the control?
I did it.
I need you to accept the...
Okay, if you want, I can pass the slides.
You can, yeah, you can pass the slides. Okay, thank you. So the presentation is divided in 7 parts. The first one is the problem. What is in bioplastic sorting we are addressing? The second part is innovation. What is our technology and how it is different from existing approaches? Then the third one is how it works. How does it function in practice? then the impact, evident results and benefits we have seen so far, then implementation, what is needed to adopt it, the future, what is next for development, scaling and collaboration, and then me and Gemma will give you a takeaway in order to remember. So let's start with the problem. On paper, bioplastics sounds great. They are made from renewable resources, they can be compostable, and they seem like a more sustainable alternative to fossil-based plastics. But when they reach recycling plants, they could create confusion. The main issue is with PLA, one of the most common bioplastics. Its chemical fingerprint, that response from near-infrared sensor, looks similar to PET, the main material used for plastic bottles. That's a big problem because sorting machine relies on near-infrared technology to recognize plastics. If the machines can properly sort PLA from PET, then PLA gets sorted into PET fraction by mistake. Even a very small amount of PLA mixed in PET fraction can damage the recycling process. It lowers the value of recycled PET, and recyclers may start to reject the whole batch. Can you pass the slide, Gemma? So instead of helping us move toward a circular economy, bioplastics could be actually contaminating recycling streams, causing waste and financial losses. To make matters worse, bioplastics are rarely separated out for composting or chemical recycling either. So in practice, they often end up being burned or sent to landfill. Why this matters more and more? At the moment, bioplastics are still a small fraction of the waste stream, around 1%. But that number is growing, and the sorting technology we use today simply couldn't be ready for that scale. If we don't act now, the problem will get bigger. Now it's my turn to explain the innovation part.
Okay, so for that reason, at the project of MoeBIOs, our goal is to develop sorting and separation system to isolate bio-based plastic from mixed bio-based and fossil-based plastic streams, and assess how this technology can be integrated into existing waste management practices. So in this project, we focus on three main areas. That is plastic packaging from municipal solid waste and from food packaging sector, synthetic textiles, especially in PLA textile, and agricultural plastic used on farms. Okay, so to reach our goal, we work together with Leitat and PICVISA. First at Leitat, we develop advanced sorting solutions using photonics, robotics, and artificial intelligence. And here at MoeBIOs, in this project, we use hyperspectral imaging technology in near-infrared to build detailed databases of bioplastics. These digital libraries are combined with artificial intelligence to improve recognition, allowing the system to adapt when new bioplastics appear on the market. Then PICVISA will integrate these digital libraries into real sorting equipment, and it should demonstrates that bioplastics can be sorted in existing recycling lines without disruption, while improving efficiency and also accuracy. So together, Leitat and PICVISA form a strong partnership as Leitat develops the digital libraries of bioplastics, and PICVISA ensures they work in industrial conditions. So now let me explain a bit about how hyperspectral imaging works. So this technology captures a series of images at different wavelengths, creating a data structure known as hypercube. Every pixel in the image contains a spectrum, so every point of the sample has a unique spectral fingerprint, enabling precise identification and location of materials or compounds. This hypercube can be analyzed in two ways also, in spectrally and spatially. So compared to conventional spectroscopy, hyperspectral imaging technology not only identifies compounds, but also locates them spatially in images. And regarding to conventional RGB cameras, hyperspectral imaging systems analyzes a wide range of wavelengths, so it reveals features that in RGB are invisible, as it only analyzes 3 wavelengths in visible range. Okay, so this technique is non-invasive, gives spatial and spectral information, can be used from micro to macro scales, and it is useful for quantification, discrimination, classification, detection, and also to measure compound size. Our system here in Leitat captures light in the near-infrared ranges, as I said before, that covers from 900 to 1,700 nanometers, offering 224 selectable wavelength bands and a high spatial resolution of 640 pixels. From the image analysis, we create algorithms to identify different compounds and create predictive models to support informed decision-making. Okay, so to finish with this part of how hyperspectral image works, so that technology are usually applied across different fields, including recycling. That is one of the fields that we are doing here in this project that can identify and classify plastic types. It also be applied to detect and classify microplastics, also to medical applications, textile industry for the detection of material types, authentication domains, revealing under drawings and hiding layers in artworks, and also for food quality, for example, to the detection of meat composition and foreign materials. Okay, so now let me share with you the initial results that we have obtained so far in developing optimized sorting and separation system. As I mentioned before, we focus on 3 main application areas: plastic packaging, textiles, and agricultural plastics. So for plastic packaging, we analyze hyperspectral data from both fossil-based and bio-based polymers that are shown here in that table, and we obtain also the spectral reflectance. The goal here was to see if we could detect clear differences between them in the near-infrared range. So by normalizing the spectra and applying statistical analysis, we identified the wavelengths where the differences are the strongest. Then, before using any supervised and classification model, we explore with principal component analysis, which helps us to simplify the data and highlight the variations. And the results were very positive. So here in this PCA plot, we can see that bio-based plastic that are the green dots and fossil-based plastics that are the blue dots appear in separate groups. So that means that near-infrared combined with PCA can successfully see variation between them, which is an important step for automated sorting. Then we also test bioplastic packaging samples from the food sector, both in clean and contaminated conditions. The PCA analysis showed that contamination didn't significantly affect the spectral response. For example, clean and dirty bottle caps appear very close to each other here in the PCA plot. And the same happened with cups. This demonstrates that the system can recognize the materials even when it is not perfectly clean. Okay, so in addition, we carried out a preliminary sorting test in the laboratory. First, we recorded reference spectra from clean samples. Then we test mixed and contaminated samples and compared them with these references. As And as you can see in the image on the right, the top image shows the RGB picture of the contaminated samples, and the bottom image shows how they were classified using their near-infrared reflectance. The system was able to correctly identify the plastics even when they were dirty or mixed. Although the method can still be improved, the results are very promising, showing that near-infrared technology can support real sorting process under realistic conditions. Okay, so for textiles, we analyze PLA-based samples with the hyperspectral camera, and by applying also statistical methods, we identify specific wavelengths that change when another material is present. And using the selected wavelengths, the analysis showed clearly differences between the samples in the PCA plot. So here in this slide, there's an example of PCA that the red dots represent samples containing wool, while the blue dots represent samples without wool. This demonstrates that the method works well for detecting the presence of different materials, as you can see that they are clearly separated into groups. The next step here will be to go further, not only detecting presence, but also estimating the amount of each material. We also plan to expand the study with more samples, pure reference materials, and to examine the effect of colors. Now, finally, for agricultural plastics, we have already collected samples, but the number is still limited. So the analysis will be performed once we have a larger data set, so more results will come in the next phase. Okay, and now I'm going to talk about the robotic side. Here at Leitat, we are developing a pilot line to detect and sort different types of bioplastics. The system is built around a modular conveyor with a 3D camera, an hyperspectral camera, and a robot arm that automatically picks the plastic to be sorted. Here is how the process works. So as the plastic moves along the conveyor, the 3D camera captures light and detects their position. And based on this image, the plastics are identified and labeled. And next, the hyperspectral camera analyzes the plastic to determine their material type. And finally, the robot arm, using an automatic algorithm, calculates the best position and picks up the plastic to be sorted. So now it's the turn of Carles.
Thank you, Gemma. So how we can implement it? Luckily, there are solutions and they don't always require expensive new machines. They are implementation from the point of view of the machines themselves and from the point of view of the sorting plan process. First, about the detection technology, as Gemma said, hyperspectral imaging, which provides almost a continuous response of the spectrum, not only some image as multispectral sensors do. Hyperspectral imaging can pick up little difference between, for example, PLA and PET. And PICVISA has opted for this technology since we created our FIS plastic sorter. And I know that most of the optical sorter manufacturers, they are already use this type of sensors. So here there is no extra cost from the hardware side. Apart from hyperspectral imaging, we can use other tools. For example, AI. The goal of AI is to train sorters, not just to see the spectrum, but also combine it with other clues like shape and color. And PICVISA has more than 3 years of experience implementing AI algorithms in optical sorters to improve their efficiency. Another option is adding tracers, which are invisible markers in the plastic that sorters can easily detect. This point doesn't rely on us. because we are not plastic manufacturers, but we have already the technology to detect them. From the second part deals with adapting sorting process in sorting plants. Some facilities are already updating their equipment and adding manually quality checks, but this manual check requires training. And another adaptation could be in regions where bioplastics are more common. It could make sense to set up dedicated sorting lines for them. And the last one could be a bale or a stream monitor in order to scan, for example, PET streams or bales before they are sold. In this way, we can keep contamination out of the system. And then we will talk about the future steps in the MoeBIOs. Can you pass the slide, Gemma? You start first?
Yeah, if you want. So
Okay.
in the next steps of the project, our focus will be on refining the classification methods to achieve more precise and reliable results. We will also work on challenging samples such as black samples, which are difficult to detect with near-infrared. And to help with this, we will combine near-infrared hyperspectral imaging system with laser-induced breakdown spectroscopy. This technique uses a laser to eliminate the tiny surface of the plastic and helps to the hyperspectral imaging camera to read the light signal that comes out, which tell us about the chemical composition. So we think that this method could be useful for black plastics because their dark color absorbs the near-infrared light, making them difficult to analyze. And with LIBS, we can still identify the material based on its chemistry, not its color. So what else? So we also plan to test the technology under real production scenarios, where we will evaluate the performance of the automatic picking systems and grippers. And in parallel, we will work with our partners to study how this solution can be integrated into real waste treatment plants. And finally, as a technology center here in Leitat, we will continue to support companies in developing innovative solutions and improving recycling processes, ensuring that our research has the real impact on the industry. And
yeah. And within the MoeBIOs project, PICVISA is focusing on improving the way we sort bioplastics. Apart from, I didn't write a point, but apart from implement hyperspectral imaging libraries from Leitat in our machines, which is the first, and I think is the most effective steps. Other steps would be, first we will carry out sorting simulations under real operation conditions in our test centers, excuse me. This allows us to test new detection methods before rolling them out to actual waste management plans, reducing risk and ensuring that the solutions are truly practical. Second, we can explore how to tackle the black plastics challenge in a different way from Leitat, which are because black plastics are majority in agriculture sector. These materials can be detected with mid-infrared technology, but I can advance that the major drawback of this technology is the cost. I would like to say that this is not a problem specific to bioplastic, but to all plastics. And finally, by applying, for example, deep learning, we can make the optical sorter smarter without replacing existing machines in case hyperspectral sensor is not enough. So within MoeBIOs project, PICVISA role is to take the concept presented before and translate them into workable solutions that waste facilities could adopt in the near future. So next slide, Gemma. If you want, So the main takeaway that PICVISA can give you is the bioplastics don't have to be a problem. With a smarter use of near-infrared technologies, software updates, and some process changes, we can make sure they are sorted correctly. And the good news is this doesn't always require massive investments. In many cases, it just matters of upgrading the software of existing machines and teaching them to recognize the new materials. If we do that, we can keep recycling streams cleaner, avoid costly contamination, and support more sustainable future for plastics.
Okay, and I will add also that near infrared in hyperspectral imaging technologies have the potential to identify and sort bio-based plastic quickly and accurately, even when they are mixed, dirty, or hard to spot, contributing to more effective and sustainable recycling. And that's all. Thank you for your attention.